Here we're going to work with sequences and look for and describe patterns and use those patterns to predict what the next numbers will be. All right, first of all, a sequence is any list of numbers in a certain order that has a set order to it. For example, 0, 1, 2, 3 is a sequence. It goes up by 1. 2, 4, 6, 8 is a sequence because it goes up by 2. Any list of numbers that has a certain pattern to it is a sequence. Every number that's in that sequence is called a term, right? We call this, for example, this would be term 1, this would be term 2, this would be term 3, and this would be term 4. So each number that's in the list is called a term in the sequence. An arithmetic sequence is a sequence in which each term is found by adding the same number to the previous term. And that will be many, not all, but many of the sequences we'll look at. So we'll start with arithmetic sequences. So what you're going to be asked to do is take a look at a sequence of numbers, find the pattern, and then use it to tell the next three terms. So as the directions say, describe the relationship between the terms in each arithmetic sequence, then write the next three terms in each sequence. So let's start with the top one. It's 0, 5, 10, and 15. I can see that each number, we're skip counting by 5s. Each number goes up by 5. So for my description, I'm going to say each time we're adding 5. That's my description of the pattern. Now, I'm going to use that to say the next three numbers. Well, 15 plus 5 is 20. And 20 plus 5 is 25. And 25 plus 5 is 30. So my next three numbers are 20, 25, and 30. Right? So my description is add 5, and my next three numbers are 20, 25, and 30. We'll go over to the right side here. We have 14, 41, 68, 95. A little bit trickier. Probably doesn't pop into your head right away, but a good place to start is by subtracting the first two numbers. I have 41 minus 14. Looks like that's a difference of 27. Let's try the next one, 68 minus 41. I think we found it. It looks like the pattern is add 27. All right, so now I can do that. Now that I know what the pattern is, I can do that to take 95 plus 27 is 122. And 122 plus 27 is 149. And my last one, I'm going to have to slide over here. 149 plus 27 is 176. So my description is add 27, and my next three numbers are 122, 149, and 176. Let's look at one last example that has decimals involved. I have 5 and 1/10, 6 and 2/10, 7 and 3/10, 8 and 4/10. It looks like we're adding 1 and 1/10 each time. So I can use that to say 8.4 plus 1.1 is 9.5, and 9.5 plus 1.1 is 10.6, and finally plus 1.1 one more time is 11.7. So my next three numbers should be 9 and 5 tenths, 10 and 6 tenths, and 11 and 7 tenths. So that's describing the sequence and extending it, telling the next three numbers. That works as long as we're going in order. But we're also going to look at how we can use algebra now to skip ahead. What if we don't want to know the next three numbers? What if we want to know the 20th number or the 50th number? We don't want to have to take the time to do this 50 times. So we're going to look at how we can use algebra. And the way we do that is we go back to this idea of term numbers. For example, in the sequence 2, 4, 6, 8, 10, the 2 is term number 1. The 4 is term number 2 because it's in the second position. The third position is 6. The fourth position is 8. And the fifth term is 10. And when we do that, we can write those numbers in a table, and you'll start to notice a relationship. 1 gets me 2. 2 gets me 4. 3 gets me 6. 4 becomes 8. And 5 becomes 10. So what relationship is there between what number term we have and what value, what the actual answer is? What's the relationship between the position and the value? And you can see whatever order it comes, whatever place in line it falls, if you double that number, that's the actual value of the number. The reason for that is we're adding by 2. 2 plus 2, 4 plus 2, 6 plus 2, 8 plus 2. So that amount that we're going up by turns into the amount that we're going to multiply to skip from the position to the value. So let's look at a couple examples of this. Right. Let's look at a couple examples. It says find the 40th term in each arithmetic sequence. Again, I don't want to list out, I see 4, 8, 12, 16. I don't want to list out 40 numbers to get to the 40th term. I just want to know what's the 40th number in this list. So what I'm going to do is start by listing, this is term 1, this is term 2, this is term 3, and this is term 4. All right, so how do I get my first number is 4, my second number is 8, my third number is 12, my fourth number is 16. What relationship can you see? Take a look. How much are we going up by? A lot of times that helps. We're going up by 4s. And sure enough, if you take the number 4 and multiply it by the term number, 4 times 1 is 4. 4 times 2 is 8. 4 times 3 is 12. 4 times 4 is 16. So if you multiply the term number times 4, you'll get that term. So if I want to skip ahead to the 40th term, I can do 4 times 40, which equals 160. So I know without having to list out 40 different numbers, I know the 40th number in line will be 160. Let's look at the next example. Here I have 6, 12, 18, 24. I want to know what is, once again, the 40th term. I have term 1 is 6, term 2 is 12, term 3 is 18, and term 4 is 24. What's happening here? Take a look at how much we're going up by each time. 6 plus 6 is 12. 12 plus 6 is 18. 18 plus 6 is 24. That's usually a pretty good indication of what you're going to be multiplying by. Let's try it. 1 times 6 is 6. 2 times 6 is 12. 3 times 6 is 18. And 4 times 6 is 24. So this time, my algebra rule becomes 6 times the term number. So if I want to know the 40th term, I take the number 6 and multiply it by 40. 40 times 6 is 240. So the 40th term would be 240. Using an algebra expression to describe the pattern, and then using that pattern to skip ahead to predict any number in the sequence without having to make the entire list. Let's do it one more time. 13, 26, 39, and 52. I can see I'm going up by 13s. 13 plus 13 is 26. 26 plus 13 is 39. And 39 plus 13 is 52. So if I call this term 1, this term 2, this term 3, this term 4, I'll see it again. 1 times 13 is 13. 2 times 13 is 26. 3 times 13 is 39. And 4 times 13 is 52. So this time, my algebra expression is 13 times the term number. So if I want to know what's the 40th term in the pattern, I'm going to do 13 times 40. And it looks like when I do 13 times 40, my answer is 520. So the 40th term in the list is 520. Using an algebra expression, looking for the pattern, and then describing it with an algebra expression instead of using adding just plus, 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 will help me be able to skip ahead. If I can use how much I'm adding by and use that to describe it as an algebra expression using a variable, I can skip ahead to any term. Again, another way that using the algebra will speed things up for me. The last type of sequence we have to look at is what's called a geometric sequence. In a geometric sequence, each term is found by multiplying the previous term by the same number. And we're asked once again to write the next three terms. So let's look. This time you notice our numbers aren't going up by the same amount. We go from 5 to 10, well that's plus 5. 10 to 20, that's plus 10. And 20 to 40, that's plus 20. So this time, it's not an arithmetic sequence because it's not going up by the same amount each time. This is called a geometric sequence. The way we get the next number in a geometric sequence is by actually multiplying the terms themselves. So for example, in this case, it looks like the pattern is 2 because if I do 5 times 2 is 10, I can then do 10 times 2 is 20, and 20 times 2 is 40. So if I continue that pattern, I have 40 times 2 is 80. 80 times 2 is 160. And 160 times 2 is 320. So in this case, my next three numbers are 80, 160, and 320. The thing you'll notice about a geometric sequence compared to an arithmetic sequence is that they go up much faster because we're constantly multiplying bigger and bigger numbers by 2. How about the second one? The second one is 3, 9, 27, 81. What pattern do you see there? If I take a look at it, I see that 3 times 3 is 9. I see that 9 times 3 is 27. And 27 times 3 is 81. So my pattern is each time I'm multiplying the previous number by 3. So I can take 81 times 3. We'll do that over here. 81 times 3 is 3 and 24, 243. And now I take 243 times 3, and I can do that one. 243 times 3. It's 729. And 729 times 3 is, looks like 2,187. Again, you'll see how quickly these numbers shoot up on you compared to arithmetic sequences. So we have 243, 729, and 2,187 are my next 3 terms in this sequence. We'll take a look at one last example and finish up with geometric sequences here. Take a look at the number 2, 8, 32, 128. What's the sequence here? What is the relationship? Did you find it? Looks like it's times 4 each time this time. So take 128 times 4. It's 32. 2 times 4 is 8. Plus the 3 is 11. 1 times 4 is 4. Plus the 1 is 5. We're already at 512. And we'll take 512 times 4. 2 times 4 is 8, 1 times 4 is 4, and 5 times 4 is 20. Now we're up to 2,048, and we have to take that times 4. 4 times 4 is 16, plus the 3 is 19. 0 and 1. Looks like we have 8,192. So my next 3 numbers are 512, 2,048, and 8,192. That's geometric sequences. So just to summarize the 2 different types of sequences, you'll see geometric sequences are going to go up very quickly, get bigger and bigger because you're multiplying the term number itself times a certain number each time. Where arithmetic sequences won't go up quite as quick because you're multiplying the term times whatever the pattern is. So slight difference there in arithmetic and geometric. But in both cases, you're looking at a sequence and looking for a pattern to describe the pattern. That's most of what algebra is looking for patterns and continuing patterns.